believe in solid-state physics, photosynthesis, and maybe something that has been presented by Jerry at the moment. So I talk about plants, optics, water, band gap engineering. I mean, study interface, energetic interface between different materials, and electrical charge separation, and get to some conclusions. Well, 4 billions of years ago, the atmosphere had about 10% of CO2. Today we have only about 500 ppm. It's very little. And 2 billions of years ago, oxygen started to be produced on Earth here. So at this time, from this time up to now, oxygen increased and ozone increased too. I have something to talk about ozone layer because there's no ozone hole, there's no ozone layer, but I will leave it to talk later. And our water is always present in our life, and we don't know where it does come from. So it starts from 2 billions of years ago with this kind of atmosphere, with the help of the sunlight, and maybe in a powder of water with 2 different materials, A and B. And in this condition, with the help of something, we could get the first charge separation on Earth. There, the life started. We don't know how. And life evolved. And we get today, starting from the first charge separation here, and a man walked on in his way. And today we are here asking ourselves why plants are green. We don't know why. It's not because of chlorophyll. And we have so many questions. And we don't know how charges are separated on trees, on leaves. We don't know how it's done. It's performed. So, 2 billions of years ago, nature created a way to separate oxygen from water. So it's in the photosynthesis process. So we have the charge separation, we have the catalytic effect for O2 separation from water, and the catalytic effect from negative charge for CO2 to create the biomass. And I ask myself, how many mechanisms we have for charge separation? Do we have 1, 2, 3? In my opinion, we don't have too much. Maybe some or 1. And water. What's the role of water in this development of the photosynthesis process of life, etc.? Photosynthesis is a beast that we think that we know it. Because we know the input and we know the output, but there is a secret, 2 billions of years, secret process that we don't know how to get negative charge separated from positive charge. And another problem is that according to the experimental results, plants absorb about 78% of the sunlight. This is too much, so we have to look for where is the problem, where do you have an answer for this? And we have light coming from the sun, and we have reflection, transmission, and we have a big problem here for the absorption, because 78% is too much. And inside we have, of course, water, and we have molecules, and we have to take care about these experimental results for plants. So these are reflection and transmission experiments from blue deer near ultraviolet. And so up to the green color here, you have this quantity here. So for reflectance and transmittance, we get about, taking from these two, we have about 55% of green color for plants. And we say that the plants are green because of reflection. It's not. And more, if you take this curve and you take for reflection and transmission, we take the surface both, we get about 22% of reflection plus transmission. It means that for absorption, we have about the surface, about 78%. This quantity, we boil the water inside the leaves in a sunny day. It means we need something much more important to take the energy coming from the sun and to take it from the leaves. So it's impossible with this experimental results to say that, well, the leaves are green because there is reflection, and you have to take care about the experimental results we take from molecules separated from water, and they say, well, here we have the absorption for the chlorophyll, and as we don't have absorption inside this region, the green region, they say, well, it's green because it's reflected. But this is molecules separated from water, from the system. So in physics, normally, we take care of this, and we have to work with the natural leaves and not from proteins separated from them. So it's not reliable experimental results for the photosynthesis process to get to the conclusions. Most of the books on photosynthesis, they show this picture where we have the sun coming here, and the photosystem 2, photosystem 1, and we have charges always going somewhere, like here, negative charge, positive charge, etc. For me as a physicist, if a negative charge goes this direction, I need an electric field in this direction, because if I accept without this electric field, I mean the driving force, I'm violating physics, I'm violating nature. So there's a big problem, and these are experimental results. We have about, between this side and this side, we have about 50 millivolts. And this is 6 nanometer chip, and so you have a very big electric field between one side and the other side. Is this easy so? Is it later? I don't know. But we have to discuss a lot about this. This is another picture of a leaf where I will take this rectangular piece here and talk something about it. It's the dimensions here, okay? It's 18 by 15 nanometers. So if I take this and I count the number of proteins inside it, I get to the conclusion that I have something like this one. So I have this quantity of chlorophylls plus carotene, and they are about 1 nanometer separated by 1 nanometer. In this case, if I consider that I have charges in this system, this charge, we need to know what we call the width function, or the IT of a charge. So this is so large, it's 5 nanometer, about 5 nanometer. So when this system absorbs light, I have to consider that each charge has its own ID card. It means this wave function. The bigger probability is here, but it can be here also. So I have to consider all this. they consider that the negative charges are already separate from positive charge. But I have to consider that they have an extonic energy, an attraction energy. They cannot go away. They need to be in the system. I have to consider this protein related to this protein to see if it fits. It's what we call the band gap energy for each one. And if we consider this band gap energy for each one, I can say, well, in this condition, it can separate charges. So, in this case, we will never get charge separation for free. Never. It's impossible. Okay? So, this cyclonic attraction must be considered, and the nanosize of the proteins has to be considered. And when this molecule absorbs lights, you have the negative and the positive at the same time. You have to consider the wave function, because this is quantum mechanics, because a nanometer size you have to take into consideration. And all this must be considered when you talk about photosynthesis, when you talk about the process inside it. And of course, you have to consider water. This system is immersed in water. It's changed everything. So up to now, we have two big problems to explain photosynthesis. The driving force to separate negative charge from positive charge is not present. The spent energy to separate the negative charge from the positive charge is not present. Two big problems from physics, from nature. The conclusion about the photosynthesis is a lot of questions. And this part is never considered if we cannot take water from the leaves or the plants and say, well, it works like this. And as the molecules and distance between the molecules are nanometer size, we have to consider quantum mechanics, tunneling, and etc. So let's see some ideas about from solid-state physics. What does it mean, band gap engineering? Band gap engineering is responsible by how this device will have this one is considered as band gap engineering. So here I have a system where I have the conduction band or LUMO, the valence band or LUMO, and I have to consider that there is a density of states. It means it's like here you have you're seated, but you have a density of energetic states in each part of this classroom. So density of states is something like this. So you can occupy different electrons here, 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 and the same for the valence band. The valence band holds electrons, but it holds also holds is a lack of an electron. It means positive. So this is a part of what we're going to talk about. When we excite this system, we can have an emission from this density of states to this density of states. And also, I can have doping effects. We can have defects in the middle, in this part here. So, I will represent this bottom here or bottom here as a flat band because it's easier. But normally we have this curve. It's look like a parabolic curve. So, we have this doping or defects inside, and according to two Nobel Prize in physics and in chemistry, we have only three kinds of relative position between one material A and another material B. one, we built these LEDs. Everything we have in solid state, we can build like with this type 1, this one. And then we have type 2, and we have type 3. So we will talk about this one. This one, that is utilized for many explanations, physical explanation, or even in the photosynthesis field, it does not exist. It means that the ground state energy, because we don't know the relative position, we put it like a ground state energy. It does not exist, the ground state energy. With this ground state energy, we cannot say that charges are moving this way, or we can separate charges. So when you have several materials, we have always barriers or not barriers for charge traveling from one material to the other. Because we're looking for a system that can separate charges. So this is what I'm doing here. I'm exciting this electron from here to here. It thermalizes and it can emit light, like this one. So we have to consider that both they have this attraction, excitonic attraction. And for inorganic materials, this attraction can be very low, few million electron volts. But for organic materials, it's much higher. And we will see that we can get much higher values for this attraction between electrons and holes. So this photoluminescence peak is not symmetric because of the density of the shape of the density of states. And when we talk about interface, this excitonic energy, it can be much higher. I will give you here an example of a material A, B, and this is an excited system. When he fell down, here we have an energetic step, and this fell down here, and this fell down here, we have always what we call band bending, because this one is falling down here, it's creating a non-equilibrium electronic system in this side, and the same for this side. So this band bending is a variation of the potential, and the variation of the potential give me what we call an electric field. If I have the electric field, I have the driving force to separate charges. So I will give you an example of one flat interface for this type 2 interface, energetic interface, this condition. So in this case, I excite this system. These are semiconductors. I have only the emission from the interface. In this case, this emission give the electrons are here and the holes are here. And I see a very little emission from this material. In this case, the emission peak is quasi-symmetric. Note that this is a very low temperature. And it is quasi-symmetric and is a very dense peak. And calculation for the exciton, it means the attraction between the electron and the hole, it's about 76 millielectron volts. And for 3D system, it means the core shell system for quantum dots, it much higher, is double this value. And for organic solar cells or organic LEDs, we need the emission. For solar cell, we need the separation of charges. And we built this sandwich as starting of many layers. You can see that they use this kind of band gap engineering. to build, to have many colors. And these colors comes from the interfaces. And the same result for separate charts is the work by Professor Olivier that construct many solar cells using this band gap engineering process. Well, our model to show how it does work to separate charts. I have here two materials. I will shine only 4 photons in this system, and these photons they turn around because of the thermal energy, and these 2 they fall down, and as they have a very high attraction, excitonic attraction, even if they are separated in space, they recombine and they have the interface emission. So here you have this band bending. This band bending, you send this one this way, and you send this one this way. I have here the driving force to separate both charts. So these are separated. But here we have this band bending like this. They send these 2 guys here and these 2 guys here. And so they recombine at the interface. And the same for the other 2. In this case, for photons, I collect only 1 pair separated. It's not efficient, but it's enough for the photosynthesis process. The photosynthesis process needs only 5%. Only 5%. So, and I'm trying to show that maybe the interface emission gives the color for the plants. It means there is a lot of energy, optical energy, that is lost here at the interface of those materials. And more, with this condition, with this band bending, I have the driving force, I have the lost energy at the interface, and I can do the process of to build the biomass or split the water with these charts, and the electric field, the calculation and the measurement of this electric field here give me about 25 volt percentage. It's a very high field because it's inside the interface, almost inside the interface. And in this case, I have the wave function for electrons and the holes. They enter the interface about tunnel, about each one, it means 3 nanometers inside one of the other. This is why we have this interface emission very strong. I will compare this now. I give an example of flat interface. Now, something that is called porous silicon. It's like a sponge system, and they are built like this one. Silicon inside, 2 nanometers. Silicon outside is not SiO2. It's a very bad quality silicon oxide. I will represent here the quantum dots, the silicon, and the silicon oxide, the band gap here. And the forbidden gap for this one is about 1 electron volt. For silicon oxide is between 10 and 13 electron volts. And also, we have to consider that this system has a lot of defect or energy levels in between this conduction band and the valence band. In this case, I can get factory interface, and I can get light emission, visible light emission from silicon, because silicon does not emit light. It's a very poor system for optical application. It has light only with the presence of something like this one. So it comes from the interface. I try to link silicon oxide, porous silicon, the first example I give, and show if I have something that I can link with is presented here in this conference, like the extrusion zone. So here you have the nothing absorption curve. a big peak here, it means that a very big, it's transparent, very big band gap. But I have this region about 3 micron, very strong absorption place. So maybe this explains why with the 3 nanometer excitation at 3 micron excitation, I get Professor Borek get this very big exclusion zone. And if I take nothing and I take water and I put inside each one some sort of defects or energy levels inside, I can see here that I have many possibilities of this band gap engineering, because I can be exciting. This one is type 1, but this one and this one is type 2. I have a lot of possibilities here if I get this configuration for the band gap energy presentation. So they can be considered as traps or energy levels. And in this case, shining light, we get negative side, positive charge on the other side, and both is striking because negative charge and positive charge, they should get together always in physics, and with many questions to me. And we are trying to work out these questions, and with a loop, different loop, as a physicist, solid-state physicist, and we are going to analyze all this, try to make all these experimental results to see if we can explain it. Because if we have our model, we have to test it, we have to prove that it works. So in this case, with the same system, and trying to have the driving force and to separate, to have the spent energy to separate charges with the light shining on, we should have an electric field in this sense for the charge separated system, because the external electric field is in this sense, because you have plus here and negative here. And we have another problem. This is a picture of what we would like to have. But if water is going inside the nature, we are creating a second interface. And it may be material A, material B, material C. 3 systems. It's not so easy to work with 3 systems. So another thing we should look for is if we have, when we are shining light, if you have an interface emission. Because, and in this interface emission, we normally, if you have this system, the band gap engineering like this one, the emission from the interface has nothing to do with this one and with this one. It's just an interface property, electrical and optical property. If you have the answer that we are seeing some information from the interface, maybe we have part of the answer for the system. So, as I said, we are going to work with many of these experimental results, including X-ray experiment, change the temperature, guide, okay, and try to put all this inside the photosynthesis system, but with water. Without water, it's not the same system. We cannot get the answer. And to the question of our title, I should say that water is a very simple molecule. So we skip it. We cannot cannot study without water. We have to make to put it in alcohol or acetone, because with water we are destroying it. And maybe if we can get to this answer with the help of many people, including the group of Professor Poller. Up to now, we are seeing photosynthesis like this. Why? Without the glass. It does not fit, it does not get this form. So we have many difficulties, and if we work with scientific consideration, we can get the answer. We have a hard work, maybe many of you, and I'm not going to stop here because it's the end. I'd like to show this one. When I'm exciting this system here and this system here, make some charts come from here to here, from here to here, etc. We have to consider something that we can do it differently, because electrons can jump directly from here to here. They cross the interface. And in this case, I can have the crossing of charges like this excitation like this, but I can also do differently, excite just the interface. And if for instance, the green color of plants are green because green is going on and coming back, in this case, we see the color of the green color because the green color is not reflecting, is absorbing and emitting the same wavelength. And if I'm doing something like this, they are working with memory or energy quantum information. When we have this attraction and recombination, excitation in the same sense. So, thank you. Please.
Regarding emission from the interface, we actually made some measurements of fluorescence, and we found that there is a fairly broad spectrum with peaks at certain wavelengths, and those wavelengths are in the visible range, and some of them include green. So I'm not sure if you've seen that paper, but we produced it about 5 years ago. So there is some emission. I'm not sure how it relates to your emission, but perhaps it's relative.
Normally, if it's an interface emission, the energy should be much lower than the excitation.
Yeah.
So there is this in physics, you can excite it with 2 photons, 3 photons. In this case, we have to look for it. If we are having 3 photon excitation, we excite with this and energy at the same time. You have 2 or 3. In this case, you can have higher energy. Well, maybe it's much more complicated.
This energy was lower because the incident light was in the UV or visible violet and such, and produced longer wavelengths in emission. So again,
but if you are exciting with 3 micron,
no, not in this case. No,
okay.
In this case, the incident light was in the UV or violet, and
well, it's in the same sense in this case. If you are seeing green and it's broad, very broad. It's about 5 times KT
Yeah.
in our case. So like this.